So here we're going to work on problem number 25 in chapter 2. One of the issues with problem number 25 is that they don't provide you with a radius value. And in order to get some numbers, you really do have to have one. And so I'm just going to assume a radius value of 1.2 meters in the context of this problem. So in the first part of the problem, we want to find the normal force at the bottom of the ramp, which is marked as the point A. At that point, there's a normal force moving up and a force of gravity pulling down. And these two are not equal to each other because the object is in a moving in an arc, part of a circular arc there. So the sum of the forces would be the normal force minus mg, and if I was say the positive y direction, and that would have to be equal to mv squared over r if there was some fraction there of a circle. And so we would say that the normal force is mg plus mv squared over r. In order to find the velocity, I'm going to conserve energy from the top. So the energy at the top would be all potential energy, and the energy at A is going to be all kinetic energy. And so if I use my height value, which was given to me, masses cancel out, you can get the V is 2gh with the square root. And so that works out to be, it works out to be 8.75 meters per second. So there's my velocity at the top. And then my normal force, which was mg plus mv squared over r, once again using the radius to be this 1.2 meters, this works out to be 119 newtons. So there's my normal force there at the point A. Now we're also supposed to find, after the object is swung up here, the normal force at the point B. Now, in this case, the best thing to do is to arrange your axes such that the y direction is again going with the center of the circle. But now the force of gravity, if I do that, doesn't have all of its component pointing in the y direction. So my y direction is now perpendicular to, say, the ramp jump point here, and this angle is 45 degrees. Then the force of gravity would have a y component equal to mg cosine of 45, because the y component is this component on this side over here. And so now the sum of the forces would be, again, the normal force minus the gravity force, but now I'm only using part of the gravity force, and that would be equal to mv squared over r again. And now I need to figure out how to find the velocity again, and so I can conserve energy. So, if I have this is actually something that's somewhat useful to know, right? If I have a circular arc where this is r and this is r, and I've swung up to an angle theta here, then the height here is equal to r minus r cosine of 45. See, because this distance in blue is r cosine 45, because I can make a right triangle right here. And then the height would be the full distance of r minus that amount. So now, with that value of the height and using the 1.2 meters as my assumed radius, I can find a value of the height, and then I can conserve energy again. And I would say that, say, mgh at the top would be equal to, say, 1/2 the velocity at b squared plus mg times this new h here at b, so I'll call that the height at b. Right, so I can get a number for all these things. I can get a new velocity value. So my velocity value at b works out to be 8.35 meters per second. That's my speed at b. That's also the answer to part C, by the way. So the answer to part C is this number. And now I can go back up and plug this velocity for b back into my equation up here. and solve for the normal force. And when I do that, I get that the normal force is 105 newtons, using this height idea and finding the velocity at B. Continuing on, now once the object has left, here's the ramp, right? It's going to now follow some projectile motion. We want to find out where it's going to land. It's launched at a velocity of 8.35 meters per second. And if you look at all the angles, this is going to be a 45-degree launch angle. And so the x speeds and the y speeds will be equal. They'll be, because the cosine of 45 is equal to the sine of 45. So I'll have 8.35 sine of 45. Both of these are equal to 5.90 meters per second. And this height, again, is this value, which we'll call that the initial y value, is this 1.2 times 1 minus cosine of 45. And that height works out to be 0.35 meters. And so if I use my y equation of motion, I can find the time. Maybe I will call up the positive y direction, and since down is now the negative y direction, the acceleration is going to have the value of negative 9.8 meters per second squared in the equation that I have. And so if I say that eventually it lands on the ground at height 0, and it starts at height of 0.35, and it's traveling at 5.9 initially in the y direction times t, plus 1/2 times negative 9.8 times t squared. This gives me a quadratic formula that I can solve for the time. If you solve that for the time, you get 1.26 seconds. And then the range of the projectile, how far does it go? X minus x0 would be v0x times t, and v0x is 5.9, and the time is now 1.26. And so you can get a value here for how far it goes. It ends up going 8.3 meters. All right. Oh, but it wants you to that's how far it went from the launch point. But if you're looking for how far it went from the point A, right, so here's the ramp, right, and then it does this. So this distance here is 8.3 meters. If I go back and I redraw my triangle, this distance here is r times, this is theta, times the sine of 45. And that works out to be, well, if I use my 1.2 times the sine of 45, this total distance would be 1.2 sine 45 plus 8.3, and that works out to be, no, I'm sorry, the whole thing worked out to be 8.3. I'm looking at the solution the wrong way, so that's some number. All of this I'm half looking at my solution. That works out to be 8.3 meters. So the distance, the 8.3 meters, is the distance it goes from the initial spot underneath the point A. So that's how far it is launched from the point A. Hope that helps.